Welcome to the second lecture for Math 2016. So today we're going to be talking about bases. So far we've talked about linearly independent sets. We've also talked about generating sets. Today we're going to pull those ideas together. We have seen and talked about when a generating set is a linearly independent set. We've seen how to do that. When you have that, we call that a basis. So it's a generating set. It builds all of the set that you're interested in, the entire subspace that you're interested in, plus it is linearly independent. All of the vectors are linearly independent. The basis we talk about most is the one we're most familiar with, the set of standard vectors. So you know that when we have the set of standard vectors, we can build every single vector in Rn, and they are linearly independent. That is a basis for Rn. So for instance, the three standard vectors, e1, e2, and e3, are the standard basis for R3. So remember, a basis is a linearly independent generating set. As an example, consider this set W. S and T are scalars, so S, S plus T, and 0. Well, that's a subspace of R3. We talked about subspaces last time. We can calculate through this the way that we did last time, vectors for the span. So W is the span of those two vectors. That means that those two vectors are a generating set. Because they're a generating set, and because they're linearly independent, that means that those two vectors are a basis for W. Here's another example. If we have that matrix, well, we talked last time about the column space. The column space is everything you can build from the columns of the matrix. So that means that all the columns are a generating set. Okay, the column space is built from the columns of the matrix. But they're not linearly independent, these three vectors. Why not? Well, we've seen how to figure out if something is linearly independent. You row reduce it, and you see if the rank, so in other words, the number of pivot columns is the same as the number of columns in the matrix. And in this one, you can see pretty easily because column 1 is the same as column 3. So it is not linearly independent. Well, because it's not linearly independent, this is not a basis. It is a generating set. It builds everything in your column space, but it is not a basis. But here is a very important fact. The pivot columns for a matrix form the basis for its column space. So take A and row reduce it all the way to row reduced echelon form. When you do that, you're going to get this matrix. Well, look at its pivot entries. There's a pivot and there's a pivot. In other words, the leading entries of every row. We have two pivot columns here. So go back to your original matrix, your original A. Take that first column where there's a pivot entry. Take the second column where there's a pivot entry. Those two columns are a basis. Those two columns are guaranteed to be linearly independent. So those two columns are a basis for your column space. Now remember this technique. We're going to be using it quite a bit. So to get a basis for a column space, you row reduce till you find where your leading entries are. Those are your pivot columns. Go back to your original matrix and take those columns. Those columns are a basis. They are going to generate your entire set or your entire space, and they are linearly independent. And that's the definition of a basis. So for example, let's find the basis for a column space of this. So what do? We take our matrix and we row reduce it. So just rewrite the matrix here. And now let's start row reducing it. So I am going to take the easy one first. So row 1 minus 3 row 3 is the new row 3. 8, 10, and it gives me 0, 0, minus 4. And I'm going to do 2 row 1 minus 3 row 2 is the new row 2. So 3, 6, 8, 0, 0. Then I have 16 minus 30, which is minus 4. 0, 0, minus 4. And then my next step is row 2 minus row 3 is the new row 3. I get 3, 6, 8, 0, 0, minus 4, 0, 0, 0. Okay, so now at this point, I've row reduced it to echelon form. You actually don't have to go all the way to row reduced echelon form at this point. But this is fair enough in echelon form that I can identify my pivot entries there and there. What does that give me? That tells me which columns I need to take out of my original matrix to give my basis. So my basis for the column space of A is the first and third column. 3, 2, 1, and 8, 10, 4. That is my basis. Okay? So that's the technique for finding the basis of a column space. Now, that leads to a theorem. Suppose you have a finite generating set for a non-zero subspace. Okay, so you have a collection of vectors that the linear combinations of those vectors generates everything in your subspace. This says that S, your set, can be reduced to a basis for V by removing vectors from S. So in other words, if you have a generating set, you can always just get rid of some things in it to bring it down to a basis, to bring it down to a linearly independent set. If it's already linearly independent, you're done. If it isn't linearly independent, you can just find things in it that you can get rid of, and you will eventually bring it down to a linearly independent set that is a generating set. Okay? And the proof for that is from what we just did. If you have a generating set, just put all of the columns together, form one big matrix, row reduce the matrix, and pick out the ones that have pivot columns. So exactly the technique we just did. Okay? When we're looking for the column space basis, we started by taking all the columns in the matrix. We row reduced. We just picked out the ones that had pivot elements or pivot entries, and we said that that is our basis. And that's exactly the proof for this theorem. So another example. Find a basis for the span of, that says D, it should say S, for the span of S where S equals those vectors. So our theorem says if we want to find a basis, we know there's a basis in here. We just have to get rid of the right vectors, and we do that by row reducing. So if we want to find a basis, we put them all one after the other into one big matrix, and then we just start to row reduce. So I'm going to do a whole bunch of steps together here at once. I'm going to say row 2 minus row 1 is the new row 2. Row 3 minus row 1 is the new row 3. And row 4 minus row 1 is the new row 4. So instead of doing it a whole bunch of steps, I'm just doing them all at once. So here we get 0, 1, 2, 0. We get 0, 2, 2, 2. And we get 0, 3, 3, 4. Okay, so I did a whole bunch of them at once. Now I'm going to look at my next one here, and I'm going to do a whole bunch of steps again at the same time, just to save time. So row 1 minus row 2 is the new row 1. I'm going to do row 3 minus 2 row 2 is the new row 3. And row 4 minus 3 row 2 is the new row 4. If you're not comfortable doing a bunch of these at once, and you do have to be a little bit careful doing them, do it out the long way, the way we always have. So row 1 is giving me 1, 0, 0, 0. I say my 0, 1, 2, 0. Row 3 minus 2 row 2 gives me that. And row 4 minus 3 row 2 minus 3 and 4. There's my next one. Now I am going to, again, do some at once. I'm going to do 2 row 2 plus row 3 is the new row 2. And this one's a little bit messier. 4 row 3 minus 3, 4 row 4 minus 3 row 3 is the new row 4. So my first row stays the same. Twice row 2 plus row 3 gives me 0, 0, 0, 2. 0, 4, my row 3 stays the same. And now I have 4 row 4 minus 3 row 2 gives me that. And then 16 minus 9 is 7. Okay. And now finally, I can do 7 row 2 minus 2 row 4 is the new row 4 to give me this. Row of zeros. And then I'll just exchange row 2 and row 3. Again, that's one of my operations that I'm allowed to do. And I am left with that, which is now in echelon form, which is enough for me to identify my pivot points, which gives me columns 1, 3, and 4. So my basis for the span of S is columns 1, 3, and 4. 1, 1, 1, 1, 2, 3, 4, 5, and 0, 0, 2, and 4. Now, one thing to note is that you can get different bases, okay? There's all kinds of different bases. So if one person does the row reductions one way, they might get one basis. If somebody does the row reductions a different way, they might get a slightly different basis, okay? But it is going to be a subset of what you started with. Which leads to this theorem. If we have a non-zero subspace, so some subspace of Rn, and we're looking for, we have two bases. As I just said, they can be two different sets of vectors that you get. But what you will find is that no matter what basis you get, they're always going to have the same number of vectors. Okay? So a basis for a subspace is always going to have the same number of vectors, even if those vectors are different. In a sense, this is the smallest possible generating set. If you take out any more vectors, you don't have a generating set. If you add in any more vectors, it's no longer going to be linearly independent. It is the smallest possible generating set. That's what a basis is. Another example, find a basis for this subspace where Rs and T are scalars. Okay, so again, we're going to look at what V is. So what is V? We've seen enough now that we can describe V as a set of, as a vector set of vectors. So this V is equal to R times 6, 1, 0, 4 plus S times 0, negative 1, 5, and minus 5 plus T times 1, 4, sorry, that's supposed to be plus 9T, 9, and 1, where R, S, and T are scalars. Okay, so that is writing down that subspace as vectors. But that gives us our generating set. So V is equal to the span of these three vectors, 6, 1, 0, 4, 0, minus 1, 5, and minus 5, and 1, 4, 9, and 1. So now we have a generating set. We have found three vectors that generate our entire subspace. The only question now is, are these vectors linearly independent? Or do we have to get rid of some vectors in here to make it a linearly independent set? So how do we do that? We put them into a column or into one matrix. And we start row reducing. So we start row reducing this. We get 6, 0, 1. We get, okay, so I'm going to do row 1 minus 6, row 2 is my new row 2. I get 0 plus 6, and 1 minus 24 minus 23, 0, 5, 9. And I am going to get 2 row 1 minus 3 row 4 is my new row 4, 0, 15, 2 minus 3 is minus 1, then we continue this. We are going to get, continue this, we are going to do 5 row 1 minus 6 row 3 is a new row 2. Sorry, that's 5 row 2 is a new row 2. And 3 row 3 minus row 4 is a new row 4. So I'm going to get 6, 0, 1, 0, 0. Work this out. I believe it comes to minus 160 right there. 0, 5, 9, and we get 0, 0, 37, I believe. And now if we to step through it fairly quickly, we're going to end up with 6, 0, 1, 0, 5, 9. Rearrange the rows, 0, 0, 1, and 0, 0, 0. So there's a couple of steps in there, but I'll leave that to you to go through it. We end up with all three columns being having a pivot point. So the basis is all three of those vectors. 6, 1, 0, 4, 0, minus 1, 5, minus 5, and 1, 4, 9, 1. That is our basis. Okay, so again, take the vectors, put them into a matrix, row reduce that matrix, and pull out the columns that have associated pivot points. Now, I talked about how any basis that you get is going to have the same size, even though you can end up getting different bases. The number of vectors in the basis is called the dimension of your subspace. This is kind of a measure of how big your subspace is. So for instance, R2 has dimension 2. There are two vectors that generate or in any basis for R2. Rn has dimension n to generalize. we think of it a little bit more, we talked about how R2 has only 3 types of subspaces. R2 has all of itself, where it has dimension 2. It also has a line with another type of subspace that has dimension 1. And if you're in R2, the 0 subspace, this has dimension 0. From here, the dimension of the 0 subspace is 0. Even though it has a single vector in it, we say that that has dimension 0. Okay, so that is looking at the 3 possible subspaces of R2. Another example, looking at the one we just did, our subspace that we just did, we ended up with 3 vectors in it. It has dimension 3. So the dimension of a subspace is the number of vectors in any basis for that subspace. And our earlier theorem said no matter what basis you pick, it is always going to be the same dimension. It is always going to have the same number of vectors. As another example, here's another subspace. What is the dimension of this? And I give away the answer, that has dimension 3, but why? Well, what does this look like? This is a subspace where it has 3 numbers, but it says that v1 and v3 is 0. So this is a subspace that looks like this: 0, v2, 0, v4, and v5. Where v2, v4, and v5 are scalars. That's what v looks like. Okay, so what is a basis for this? Well, a basis for this is 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 0, 1. Okay. Why is that a basis? Well, those 3 vectors are a generating set for my subspace, and you should be able to, at this time, be able to tell pretty quickly that those vectors are linearly independent. So that's a basis. So the dimension of V is equal to 3. Which leads us to another theorem. If we have a non-zero subspace of Rn with dimension k, so we've talked about how to get the dimension. So if you have a subspace with that dimension, then that means that every linearly independent subset of it has at most k vectors. Your dimension is essentially the upper limit on the number of linearly dependent vectors you can have. As soon as you throw in another vector, then it's linearly dependent, which is what this second thing says. Any subset that has more than k vectors is linearly dependent. The dimension is the maximum number of vectors you can have in any subset that is linearly independent. Now, it doesn't mean that every collection of k vectors is linearly independent, because you can find linearly dependent vectors pretty easily. But if you're trying to get the biggest possible set of linearly independent vectors, that's your maximum limit. That's as far as you can go. The second theorem is very closely related to it, which says, again, if you have dimension k and you have a subset with exactly k vectors, so you've pulled k vectors out, then if those vectors are linearly independent, they are a basis. Or if those vectors are a generating set, it is also a basis. So if you have a collection of vectors, and that is exactly equal to the dimension, if you know the dimension, all you have to do to see if there's a basis, you have to check that either they're linearly independent or they're a generating set. So to show that a set is a basis for a subspace, here's the steps. Show that every vector is in your subspace. show that your set is either linearly independent or is a generating set, then show that that is equal to the dimension of your subspace. So for example, show that these vectors are a basis for V, where V is the span of those vectors. That should say span of those vectors. Okay, so we have 3 steps to this. The first step says show that every vector in here is actually in your space, in your subspace. So how do we do that? So first off, show that our vector 1, 2, 5 is in V. So take the first vector. How do we do that? Well, what's V? V is the span of these 3 vectors. So that means that we have to show that x1 times 1 minus 1, 2 plus x2 times 1 minus 2, 1 plus x3 times minus 2, 5, negative 1 equals the vector we're looking for, 1, 2, 5, has a solution. Okay, this is what we've been doing all along, trying to solve a system of linear equations. So how do we do that? We put it into an augmented matrix and show that this has a solution. So we start row reducing. So I'm going to do, again, combining some of the steps to make it a little more efficient. Row 1 plus row 2 is the new row 2, and 2 row 1 plus row 3 is my new row 3. What do I get? 1, 1 minus 2, 1. I get 0 minus 1, 3, 3. I get twice that plus that is 0, 3, minus 5, and twice that plus that is 7. Now I'm going to do row 3, row 2 plus row 3, my new row 3. 1, 1 minus 2, 1. 0 minus 1, 3, 3. And 3 times that plus that is 9 minus 5 is 4. 9 plus 7 is 16. So at this point, I've gotten it down to echelon. Oops. I've gotten it down to echelon form, and that is enough to show that there is a solution. There is a solution. So that means there's a solution to this. That means I can build my first vector from the 3 vectors in my generating set. So it means that 1, 2, and 5 is in the span of those 3 vectors, or I can just say that it's in V. Okay, so that shows that my first vector is in my set. Now I have to also show that my second vector is in that set. So show that that is in V. In other words, x1 times 1 minus 1, 2, plus x2 times 1 minus 2, 1, plus x3 times minus 2, 5, minus 1 equals 1, 3, 6. So show that that has a solution. It does. I'll leave that as an exercise for you. You can actually see it fairly easily, but that it is in there. So it satisfies my first conditions. My first condition was that to show that every vector in V is also in V. That is true. My second is to show that V is either linearly independent or is a generating set. In this case, it is going to be easier to show that they're linearly independent. So, 2 vectors show that they're linearly independent. How do we do this? Well, in this case, you might be able to see it just by observation, but really what we do is we take 2, 5, and 1, 3, 6, row reduce. So 2 row 1 minus row 2 is my new row 2. I get 1, 1, 0, minus 1, and I'm also going to do 5 row 1 minus row 3 is my new row 3. I get 0, minus 1, and my next step would, you can fill in the blanks here, but in row reduced echelon form, I have the rank is equal to the number of columns, so it is linearly independent. So that's done. Third is to show that I have to show that the number of vectors is equal to the size, or to the dimension of my space. So how do I get my dimension? I put it all into one big matrix, and I row reduce. So I row reduce, row 1 plus row 2 is the new row 2, and 2 row 1 minus row 3 is my new row 3. I get 1, 1 minus 2, 0 minus 1, 3. Twice that minus that, I get 0, 1. Oh, that's supposed to be a minus 1. Minus 3. My next step, I'll get 1, 1 minus 2, 0, minus 1, 3, and 0, 0, 0. So what do I have? There's my leading entries. I'm in echelon form now. So that means that my dimension of V is equal to 2. It is the same as the number of entries in my basis. So B is a basis for V. And we're done. It matches the 3 conditions. And finally, here are your practice problems for section 4.2. Thanks for listening.